So we were asked in the previous video to show that these are equivalent statements. So let us show that. We have P and Q, 1, 1, 0, 0, 1, 0, 1, 0. And then we would have our equivalent statement. To show that these two are equivalent, we'll have not P or Q, if and only if, not P and not Q. So we have our P and Q here, so we'll just copy those, 1, 0, 1, 0. And not P and not Q is just the opposite of that, so 0, 0, 1, 1, and 0, 1, 0, 1. So now we do this conjunction here, so I will have 0, 0, 0, then 1. Here, I will do this disjunction now, so that's be 1, 1, 1, and 0. But for this side, it's not yet done because we need to negate the disjunction. That's correct. So we'll have 0, 0, 0, 1. And as you can see, this green column here and blue column here have similar truth value. So therefore, this will be all 1. And therefore, these two statements are equivalent. And when we say they're equivalent, that would mean that whatever truth value will come here, they would have the same truth value. That would mean that whatever the truth value of the simple propositions there and the propositional variables, those two would have the same statements. Now, the truth value for equivalent statements should always see that the biconditional is true. And actually, it's not just in equivalent statements, but if there are other propositional forms or propositions in which its final column would always be true, that would mean that that statement, this entire statement, would always be true no matter what happens. And those statements would have a specific name. And there are also statements that are always false no matter what these values would be. And that's what we're going to now define our tautologies and contradictions. So, if our equivalent statements, both statements will be equivalent if that biconditional statement would always be true. Hence, we can also say that if our proposition P and Q would be equivalent and this would always be true, then we can say that P and Q are equivalent if this statement is a tautology, because a tautology is a statement that is always true. However, if we would get this and the resulting column would always be false, then we call this statement a contradiction. A contradiction is a statement that is always false. However, if it's neither always true, neither always false, or neither a tautology nor a contradiction, we call the statement a contingency. So, let's have this example here. We have the statement P and Q or R is equivalent, or if and only if, because that's a biconditional, P and Q or P and R. Pause the video and try to see if this is an example of a tautology. So, let us show. This is its truth table in its traditional method, or the long one. And here are the values. We'll not go through that because I think you'll be able to go through that when you did your own truth table. But as you can see here, all the values are true. So therefore, this statement is an example of a tautology, because all the values at the final column are true. But do take note that not all biconditionals will be tautology. We would have to show via the truth table that it would be a tautology, because it might not be. So here, we are asked to show that this is a tautology. And again, we can do that using our truth tables. So we'll have our P and Q here because those are the only propositional variables that we have. So we'll have 1, 1, 0, 0, 1, 0, 1, 0. Then we'll also have P or not P or Q. So to show that it's a tautology, that means somehow we should expect that this is an actual tautology. So let's put in our values. This is 1, 1, 0, 0 because that's just P, and just Q will be 1, 0, 1, 0. Not P would be the opposite of P, 0, 0, 1, 1. Now we need to operate this two here using OR, so I will have false or true is true, false or false is false, is true rather, true or true is true, true or false is true. And that's now what we would have to operate with an OR. So true or true is true, true or true is true, false or true is true, false or true is true. So even though this is not a biconditional statement, we were able to see that in the final column, it's all true. So therefore, this is a tautology. So this time, we are asked to show that this is a contradiction. So pause the video, create a truth table, and see whether or not this is a contradiction. Alright, so we would have now our truth table here, which is P and not P and Q. Goes, I'll have 1, 1, 0, 0, 1, 0, 1, 0 there. Then same values for P, same values for Q. My not P is opposite of that one, so 0, 0, 1, 1. And then we would now have to conjunct that one, so this is 0, 0, 1, 0. And then this one, the blue column, is what we have to conjunct with P. So this will become 0, 0, 0, and 0. All false, as we can see here. Since it's all false, therefore this is a contradiction. Oops, sorry. So there you go. So remember, if it's always true, it's a tautology. If it's, oops, there you go, always false, it's a contradiction. If it's neither of the two, it's a contingency. So those are some examples of how we use our truth tables to verify equivalent statements and to verify tautologies, contradictions, and contingencies.